In the following videos, we're going to solve the practice exam from the 1801 Single Variable Calculus course at MIT. In this part, we're going to read the problems and give the overview of the problems, which techniques and which concepts are used to solve those problems. In problem 1, we're dealing with some basic derivatives with the chain rule, the product rule, or more the quotient rule more than the product rule. In problem 2, we are asked to find the equation of a line tangent to the graph. The graph is given by an implicit definition, so we are going to deal with implicit differentiation. In problem 3, we are dealing with the implicit differentiation of a function. In problem 4, we are going to examine the requirements for differentiability of a function, which includes the continuity of a function. In problem 5, we have applied differentiation. We're going to read the problem carefully, then we're going to draw a figure that describes the problem, and then we're going to solve this. This is a rate finding problem, and we're going to use implicit differentiation since the equation of a function which will need to be differentiated will be given in an implicit form. In problem 6, once again, we'll have applied differentiation problem. We're going to need to draw a figure. This is a geometric problem, and we're going to need to find a global maximum of a certain function. This will entail finding local maximum of a function. In problem 7, once again, we have applied differentiation. We're going to need to read the problem carefully and draw a figure. And once again, we're dealing with the geometric application, and we'll need to find the differential equation that describes this problem based on the geometry of the figure. After that, well, we're given the differential equation, and we're going to need to actually check whether our geometric problem really fits or satisfies this differential equation. And in part B, we're going to use separation of variables technique to solve this differential equation. In part C, we're going to describe the curves, which is going to be straightforward from the obtained result of the differential equation. Problem 8 deals with the application of definite integrals. We're going to calculate the volume of a solid of revolution, and I'm going to demonstrate both disk method and method of cylindrical shells to derive the equations to calculate the volume of a solid of a revolution. In problem 9, we are going to deal with an approximation of a definite integral, which is actually somewhat based on a definition of a definite integral, and in particular, we're going to use a trapezoidal rule. Of course, we are going to draw a figure and proceed from that. In problem 10, we are going to deal with the concept of integrals dependent on a parameter. That is, we're going to have an upper limit of the integral, which is a variable, and this involves the concept of antiderivatives as well. In problem 11, we have two parts. In part A, we're going to apply definite integrals to calculate the length of a curve. We actually need to calculate the line integral. In part B, once again, we're going to apply definite integrals And in particular, we're going to use the Lagrange mean value theorem to calculate this, what is needed for part B. In problem 12, we are dealing with integration techniques. First one is going to deal with partial fraction decomposition, and the second one is the integration by parts. In problem 13, once again, we have integration techniques, and this case involves trigonometric substitution, and we are going to have to be careful about the limit change when we do the substitution. Problem 14 deals with polar coordinates. We need to transform between the Cartesian and polar coordinates. We're going to have a spiral, and once again we're going to use integration to find the area under the curve. In problem 15, we're dealing with limits of indeterminate forms, and we're going to use the L'Hopital's rule to find those limits. Problem 16 deals with an improper integral, and we're going to see whether this integral converges, and we will evaluate it if it converges. Problem 17 deals with a problem of a convergence of a series. We're going to use two criteria for convergence here. First, the comparison criterion to simplify the problem a bit, and then the integral criterion for convergence. In problem 18, we're dealing with approximation of a function. We're going to apply differentiation to calculate the Taylor series of a function, and we're going to use the Taylor series of a function to approximate the function. Finally, problem 19 asks us to find a Taylor series for some function by using a Taylor series for some other known function which is related to this function. In particular, this other series is geometric series, and we're going to use integration of a series to obtain our Taylor series of the function that is given to us.